Well, look at this problem, which is 2307. And the problem description is you are given some equations. And this equation array, each element of this equation array has two items. First one is the so there will be a equation a divided by 2, and first one is a and second one is b. A divided b equals to the corresponding values. So for example, the first equation, first item is a and second item is b. So that means a divided by b will equals to 3. And then the question is based on this equation and this condition. So is there any contradiction? For example, the first one. So if a divided by b equals to 3 and b divided by c equals to 0.5, and then a divided by c is also equals to 1.5. So is there any contradiction? So there might be multiple options to choose the value of a, b, and c. A equals to 3 and b equals to 1 and c equals to 2 satisfy all the conditions without contradiction. So the output would be false. That means there's no contradiction. And for the example 2, that means LE and ET. That means LE divided by ET equals to 2 and leetcode equals to 5. That means LE divided by code equals to 5. But for the third equation, that code divided by ET equals to 0.5, there might be may be no option for that satisfy all the conditions, right? Then that means there is some contradiction. We cannot satisfy all the conditions and the values here. So how to determine there is any contradiction or not? So I think one smart way or wise way to do that is, it looks like some of the, we can use the union find to, so typically we use union find to identify the connected component, but for this problem, we want to see that no matter not only there's connection between each items that exist in the equation, not only the connected, we not only need to determine the connection between each item in the equations, but we also want to quantify the actual connection between them. We want a quantitative description if the connection exists, and then we want to derive the if there's any contradiction or not. So the union find can do that. Not only can identify the connection between each given node, and if we maintain the distance between the node to the root, then we can also reach the point to quantify or determine the actual connection between two nodes. Okay, so how to do that? So let's do a quick analysis. Let me use this graph as an example. So for here, as you can see, the node A, so the right line means what I'm trying to add, and the black line here means the already existing connection between them, and the value with arrows means the distance, and the black line without arrows means there's an undirected edge between the nodes. Then let's say the root of node A is PA. That's what we're normally used for union find. The root we define here. And we also have a node for the node B. But for now, we're trying to add a condition that constrains the or quantify the distance between A and B. Or that is to say, we have one more new equation. The value of the first item is A and the second item is B. And the value for this equation is Vi. And now we found the parent of node A and node B are now same. That means there's no connection between them before. But now we're trying to add the connection between A and B. So without thinking of the distance between the node to the root, if we only think about the connection, if we only need to maintain the connection, we can just simply assign the parent of PB to PA, then that's it. But now we also need to consider the actual distance between the node to the root, right? So that's to say we want to add a red arrow here between the PB and PA. And we want to calculate what the value should be this red arrow between PB to PA. So now we have two equations here. So D dot B means the new value between the B to the root, or to the new root, or to the in the new graph, or after updating the PB to PA, or any definition. But this is a new value. That's a value we want to maintain. And so if we don't maintain from the PB side, we just add B, or we just set the parent of B to A, then this value would be Vi times dA, which is this side, BA and PA, this path. But if we do the path compression in Unified, we also can assign the parent of B to PA. So now these two paths from BA PA, or from B to PB to PA, both of this distance should be equal either way, right? If we do not do the path compression or we do the path compression. So we got the second equation, which is previous dB. That means the previous distance between node B to its root, which is PB. Now it times x, which is the distance of this red arrow from PB to PA, which is the value that we want to calculate. And both of these ways should equal. Then we can resolve x, which is equals to Vi times dA and divide dB. So this is the most important part when we're trying to union A and B, and we want to find the distance between PB and PA. After we are clear about this part, then we can just do one more thing, which is different than the usual unified. So let's first identify the parent array. Typically, I'd like to use this for the non-numeric key. I just assign the default value to no, sorry, that's not correct. So I just use a empty map, and we use default dict, and the default value is lambda 1. That means the default distance between the node to its parent, because the default node's parent is itself, so the distance would be 1. And as we can see here, the values is not actually the integer, right? It might be some float or double decimal number. So we needed to identify the epsilon for the difference. So by floating to compute the float number operations, it's not exactly same because there will be always some errors. So we need to have a tolerance for the difference, and if the difference is within this tolerance value, then we can roughly to say they are equal, but actually they're not strictly equal. So we need to analysis this tolerance because the value is always from 0 to 10. And the equation length would be 100. So that is to say, yeah, it's 2 decimal places, right? So maximum of 2. A and B length is equals to 5. Okay, lowercase English letters. Yeah, so let's just try to use some random tolerance and refine step by step. So let me use a tolerance T here. So so since it's 2 decimal and it's range from 0 to 10, let me use maybe 6. Okay. Yep. And let's build the find function. So the normal find for number is this. So if x is not equals to px, then we simply add set the parent of x to the root of the parent x, then return the px, which is the normal path compression, but that's for the numeric key. So now it's English letter, which is a string, and we might not do that way. So first we need to determine whether x is in P already or not. So if it's not in P, then we can just set the px equals to x. Then else means we already have this, or we made this before. Then we can confident to call the px here. So if x is not equals to px, so when we do the path compression, we're doing from top to down. So first we need to identify the root, which is find px, I guess. Rather than do the normal compression here, we also need to calculate the distance between the node and its root. So we do it step by step. So first, the x will times the distance between the parents to its root. So here, we are not updating px yet. So here px is the direct parent of x. So that means we do the compression step by step. So if so let's say this, if the graph is 1 to 2 to 3 to 4, in order to update the distance between 4 to 1, so we first times the distance between 4 to 3, then times the 3 to 2 and 2 to 1. And after that, we update the parent of the x to the root directly. After doing so, we get we can just return px, and now it's set to the root of this tree. Okay, this is a find function here. After doing this, we can just iterate the actual equation and do the calculation in enumerate of equations. So first we need to find the parent of x and y, and we can do this way. Find the y here. And there will be two scenarios. First is if P1 is exactly equals to P2. That means we are trying to connect the two existing connections. In order to derive if we have contradiction or not, we need to calculate the actual or the existing distance between them and check if they are equals to the new values. So how to do that? So for that, yeah, we need to identify the actual distance first. So what is the actual distance? It should be dx. So actual distance is this dx. Then divide by dy. And we want to make an assertion that we want to ACT if ACT is equals to values index or not. But we're using a decimal. We are considering of the float number, so we want to think of this tolerance. So we want to make an assertion of this, and that is equals to the assertion of calculate the absolute value of dx minus dy times the values of I, and this is smaller than the tolerance. We can see they are correct, right? So if it's bigger than the tolerance, then we think there's a contradiction. We just return the true here. And else means this scenario. So we added a connection between the existing one with the two node that is not connected yet. Then we want to calculate x this way, which x is the distance between PB to PA. So first, like the normal path compression, we assign the parent of PB to PA. But now we need to maintain one more thing, which is this. And as you can see, the PB to PA's distance is values I times dx divided by dy. So it equals to values index times dx divided by dy. If you will, yeah, that's it. So after maintain this and we union them for the find function, yeah, if we iterate all of them, we're not returning true, we can just return false, means there's no contradiction. Yeah, let me try. Okay, first is not correct. Why is that? So oh, okay, I see. So the so let's consider the equations. It should be x divide y equals to value index, and x divide y I want to make this assertion. So let's first check if our epsilon is too strict or not. Step by step. Okay, still false. So might be this. Okay. So y is dy. Okay, x divide. Yeah. So the distance. Oh, I see. So the So the lower the distance between node to its root, the bigger value this node have. Then we're assuming x is always closer to the root. So actually we want to compute, so the distance would be, the distance to the root would be actually dy divided dx. That's a issue, I guess. Okay, so let me use the second example. Yeah, it looks correct. So let's try to submit. Yeah, it passed. So let's do the time complexity analysis. Since actually we're not doing the merge by rank, so usually the time complexity for disjoint or union find is thinking of the the reverse Arcman function, and this function is very slow, will increase very slowly with the size of the operation. So let's say if we have find call and any other call like the query or the union or something, other calls, then the time complexity is equals to the alpha m times n, and this is n times this, and this is reverse alpha, or alpha function means the reverse Arcman function, and this function is very flat, since the Arcman function is increasing exponentially, and this reverse Arcman function is increasing slowly, and this value is any of the physical variable for m and n in our world. If we replace this with actual physical variable in our universal, this value will always less than 4. So we can consider this is linear to the number of times you call the found. So come back to this question. So if the length of the equation equals to n, the time complexity will be linear to n. And as for the space complexity, we use a parent dictionary, and we also maintain the distance. So the space will also be linear to the size of the equations. Yeah, that's it. So let's try to do this in Java, or I will not record that part. I will do it later. So that's it. That's this question. First we discussed about how to calculate the PB to PA, the distance. We got two equations first, based on the two different paths from the B to the root. First, we do not do the path compression. So if we do that way, the new distance would be VI times dA. And if we do the path compression, that means we assign the parent of PB to PA. So by doing that way, we're following this direction from B to PB to PA. So the distance would be dB times x. Then we resolve x by doing this. And then we maintain it here. Unlike the Euro union find, we also maintain one more thing, which is the distance between the node to the root. And we do this as well in the find function. The one more step is we also maintain, rather than assign the root to px directly, we add one more step after getting the root. We assign the value step by step until reach the root. based on the recursion attribute. So that's it. Hope you enjoy.